Hi, I'm Stefanie Kuchinsky, and I'm going to be telling you about insights into effort through the eyes, ears, and brain. I want to thank Nancy and Maria and the organizers for having this event and for inviting me. I may be an outsider to the Voice Foundation, but I hope by the end of this presentation it'll be obvious that I think that effort and fatigue are really multidisciplinary topics, and there's a lot that we can learn from each other. So I'm going to be telling you about my perspectives on effort via hearing sciences. And I'm really looking forward to the panel discussion later. Just a disclaimer as a federal employee. So why do audiologists care about effort? It starts with patients, of course. So these are some comments that are not unordinary. This is from a woman who has moderate hearing loss, who's talking about how she participates in social events and in her daily life. She reports, "I get exhausted more easily, then I avoid these necessary social interactions, even if I want to be a part of them. These challenges leave me feeling isolated, lonely, and fatigued." This quote is by a deaf individual. He says, "I went to a great conference today. It was riveting and I was hooked on pretty much every word. And then I got home and collapsed on the sofa. I'm not just tired, I'm shattered. I had to turn off my ears to rest in silence." He wears cochlear implants. So these quotes just highlight that effort is not just something that you feel once in a while, but can have these really important and profound consequences. And the idea is that when you're listening to a degraded acoustic signal, you need to engage more top-down cognitive or other resources to fill in any gaps that might exist. And that this recruitment engenders a sense of effort and ultimately potentially fatigue. So anecdotally and through experimentation, we've discovered that some individuals just have to work harder to understand speech. Even if they're correctly identifying words in our clinical tests, people with hearing loss, older adults, people with a traumatic brain injury often have to work harder to achieve that level of performance. Even people with normal hearing report difficulty in everyday situations that are really common, like at a poster session. There's the demands of the acoustic environment, noise, reverberation. There may be demands associated with listening to non-native speech sounds or complex syntax. And there may be demands associated with attention or other cognitive factors, like the fact that you're often having to multitask. And the consequence of this effort may be pretty important. So again, even if performance is pretty high, having to work harder may come at the cost of problems in other cognitive and physical functions like memory and balance. And so quantifying effort is going to be important in order to really understand what the problems our patients are facing and what are the right interventions that we can develop to target those problems. So the kinds of questions that we in the field of hearing science ask are the following, and I'm going to sort of step through these as an outline for my talk. So the first is I'll give some background on how we define and measure effort. I'm going to talk about multifaceted task demands. So how do auditory, linguistic, and cognitive demands impact effortful listening? Can we intervene? Can we alter listening effort to improve outcomes? And then I'm going to spend just a small bit of time asking, what is the relationship between listening effort and fatigue? So to start, how do we in hearing sciences define and measure effort? Probably the most well-cited model of effort came from Pecora Fuller in 2016. There's a special issue in Ear and Hearing that has a number of papers on the topic of listening effort. And one of those develops this framework for understanding effortful listening, or FUEL. And this definition gets cited in almost every paper of listening related efforts. So it is the deliberate allocation of mental resources to overcome obstacles in goal pursuit when carrying out a hearing listening task. And it's based on the Kahneman 1973 capacity limited models of attention framework. And from that, they added on a few pieces that I'm just going to highlight. I'm not going to step through all aspects of this, but just to give you a sense of what are the factors that we're concerned with that can affect effort. So to break down this definition a little bit, I'm going to highlight the word obstacles. And in my mind, that refers to the fact that there's some task that you're going to have to accomplish that have these specific input related demands. So these are the sources of noise in the environment. There's the fact that different listeners have different sensory and cognitive abilities, and a variety of other things in our environments that are going to place these demands on our particular systems. So then to highlight the word mental resources in this green box here, ultimately the capacities that we have to meet those demands that are placed upon us. And if we have sufficient capacity, well, we're good to go. And if we don't, that's when there may be problems. And then finally, I'm just going to highlight the word deliberate allocation. So not only do we have to have the capacity to meet the demands of the listening task, but we have to be willing and able to allocate them to the task at hand. So maybe I'm just not feeling it today and I don't want to engage in this task. It's really boring. You know, I'm not going to necessarily think it's worth it to allocate my attention and my mental resources to it. So just I'm going to highlight a couple review papers here that I think are really useful if you want to do some more reading on these topics. So McGarrigle et al., Zekfeld et al. Have some nice reviews on input-related demands that can impact listening efforts. And I think it's really interesting to read more about some of these murky definitions that are even within this definition of effort. So what are resources? And how do we know when listening is worth it? So I'm going to focus most of the talk on these input-related demands. And specifically talk about how we measure the impact that those might have on effort. So probably the most common ways that we measure effort is subjective self-report. So how hard was the task that you just performed? We often ask people to perform a task and measure how accurate they are or how quickly they can complete the task. And then more in terms of defining objective measures that give us better information about how effort unfolds over time is these physiological and neural measures. And these typically are sensitive to changes in the autonomic nervous system, for example. So this little diagram here just shows parts of the autonomic nervous system, and things like heart rate, breathing rate, pupil dilation, galvanic skin response are measures that people have used to try to examine listening efforts. I'm going to talk a little bit later also about some neural measures that we use to measure listening effort, particularly functional MRI, but there are many others as well. So because I'm going to be talking quite a bit about it, I'm just going to highlight pupillometry here. So changes in pupil dilation can be monitored using an eye tracker across many different types of tasks. And the reason that this has been used to measure effort is because activity in the locus coeruleus brainstem nucleus, which is really important for shifting one's arousal state and driving one's attentional state, pupil dilation has been shown to be kind of tightly correlated with activity in that system. So in this Joshi et al. Paper, what they did was in non-human primates stimulated the locus coeruleus and were able to measure a tightly linked pupil response following that activity. And indeed, when people use pupillometry, they've found that increasing auditory and cognitive demands can be reflected in this pupillary response. And again, even when performance is good or doesn't change from condition to condition, pupillometry has been shown to reveal aspects of listening effort beyond performance alone. So another way that we measure effort, as I mentioned, is through neuroimaging. And one reason I'm biased to use neuroimaging is because I think terms like effort, resources, and capacity, they're either really hard to define, or at least they've been very well argued about in the literature. So even with great models, and we do have some really good ones, they can be murky. And so in my mind, I think of neuroimaging as a type of ground truth, in the sense that instead of talking about effort, can we reframe it in terms of what are the specific auditory, linguistic, cognitive systems that are engaged when we make a task more challenging? And then the question is, how well do our behavioral and physiological measures that we have track activity within those systems? So Jonathan Peele has a nice review paper talking about, presenting degraded speech signal. What are the networks that we see classically come online? Well, of course, there's the core speech network in temporal lobe and inferior frontal gyrus. But then there's also additional attention systems that come online, particularly when speech understanding is challenging. That includes, I'm going to refer to this later, the cinguloopercular performance monitoring network. So a system that comes online to make sure you're keeping on task, you're doing the right thing, you're not making mistakes. Some verbal memory, some other attention networks as well. And so really it's activity within a whole different set of networks that might be indicative of what we're sort of calling efforts. And so there's a lot more work to be done here, but this is one of the approaches that I tend to take. Okay, so next I want to talk about how these input-related factors, as I've sort of described them in the fuel model, how those impact effortful listening. So we know that listening involves a lot of different processes, perceptual, linguistic, all the way up to sort of attentional and other kind of cognitive domains. So we talk about all these systems, but then we sort of talk about listening effort as one giant thing. And as I've been hinting about with neuroimaging, maybe what we should be doing is talking about all the different processes involved that support these functions, some of which may interact with one another and some of which may not. So to build up to this, I want to talk about the fact that, yes, many studies have examined how auditory acoustic factors impact effort. But we do our testing in sound booths, and that's great, but communication rarely takes place in isolation. We're often doing more than one thing. We often have a lot of different demands imposed upon us at once. And there are relatively few studies, at least in the domain of listening effort, that have examined interactions between auditory, linguistic, and cognitive demands that might be more reflective of real-world situations. And really, there's limited understanding right now of how measures of listening effort track these underlying neural systems that we know are engaged when people are doing challenging tasks. So I'm going to start by addressing this first red bullet here and tell you about some of the work I've done investigating some of these interactions. So the first study I'm going to tell you about was with older adults. We were manipulating both acoustic and lexical demands. So we were presenting a word in background noise at different signal to noise ratios, making them easier or harder to hear. And then we were also presenting a competitor word, and they had, or not, and they had to choose which word they thought they heard. So they might have heard the word like, but both like and line are an option, and so there's some competition when they go to make a decision. And so what we wanted to know is how these factors interacted with one another. The first thing that we saw was that there's an impact of auditory difficulty. So the pupil response was slower to peak with a harder signal to noise ratio. So on this plot right here, we have the harder signal to noise ratio in red and the easier in blue. And what you can see is that there's a sort of earlier peak here for the blue than the red. But maybe more importantly, we found an interactive effect later on in the pupillary response, particularly in the tail, that when the task was most difficult, both the acoustic demands were challenging and there was a lexical competitor, you saw the most sustained pupillary response. And this suggests that we can observe the time course of how these effects develop and the fact that there are interactive effects between acoustic and linguistic demands. Similarly, I've examined in younger adults acoustic and multitasking demands, so kind of cognitive demand. Again, manipulating signal to noise ratio for making the speech harder or easier to hear. And then participants either perform just an auditory task alone, so this single auditory, this blue line here, or they perform just a visual task, identification task on its own, this purple line here, or they performed both together. So they were doing the task either one or both. And we found that the slope of the pupil response, how quickly it came to peak, was larger if it was a harder acoustic condition or a more taxing cognitive condition. So in this case, the dotted lines are all above the solid lines, and in particular, the red lines are above the blue and the purple lines here. And again, importantly, though, there is an interaction. So the pupil response tends to stay elevated when you're either listening to a word or having to listen and perform a visual task, except in this easiest condition, so the easiest signal to noise ratio, and when you're only listening for the word, that tends to fall back to baseline more quickly, while these other pupillary responses stay elevated. And again, that suggests that we can track the time course of how auditory and cognitive demands might unfold during a listening task. So the next point I wanted to make is that there's limited understanding of how what we're calling a measure of listening effort, is that really tracking the neural systems that we know are engaged during challenging listening tasks. So there's been some work, some of it related to listening and some not, showing that average pupil dilation has been linked to specific regions of sensory cortex and that cingulopericular attention network that I mentioned earlier. So I'm going to just step through that briefly. So we did a study a few years back looking at, we just had people lie in the MRI scanner with their eyes open for about 9 minutes. And, activity in the brain just ebbs and flows over time, as people attend or become inattentive, mind wander. And what we wanted to know is, even just at rest, is there a relationship between pupil dilation and the attention networks that we know can, like I said, change over time? And in fact, what we see is that greater pupil dilation is associated with activity in the cingulopericular attention network. So right here, I'm pointing to the anterior cingulate, and partly here is the frontal operculum and anterior insula. And there's some visual cortex activity because obviously they're looking at a screen as well. In a visual-based Stroop task, the study found, again, that pupil dilation on average was related with greater activity in the anterior cingulate cortex while performing this cognitively demanding task. And in a speech recognition task, they found similarly greater pupil dilation associated with more activity in bilateral auditory cortices, as well as this anterior insula frontal operculum area, part of the cingulopericular network. But importantly, these previous studies were just looking at overall pupil dilation and not how this relationship changes or how sensitive pupil dilation is to variations in task demands, so easier versus harder listening. So that was the point of this study. So this is the same pupil response I showed you before. What we then did is, we were recording that while people were in the scanner, so we could link these responses to the specific neural systems that were being engaged. So first, the first contrast I'm going to point out is listening to a harder signal to noise ratio versus an easier one. And again, you see this classic cingulopericular attention network. It's sort of if you don't see that when you have a hard versus easy task, you're kind of doing something wrong. So that's good to see. But our real question was, how do individuals who show a larger pupillometry effect show that they are more affected by signal to noise ratio in terms of pupil dilation? Do they show a similar or related change in neural activity? So what we have here in green are the regions that individuals who showed a larger pupil effect tended to recruit even more cortex associated with these frontal attention regions. And finally, that effect that we saw, that some individuals are more affected by not only the acoustic demands, but also by the cognitive demands as well. For those individuals who showed a larger effect in terms of pupillometry, we also showed different regions of cortex being engaged for those individuals. So not just the cingulopericular network, but this orbital frontal cortex, visual cortex, some regions that are involved in things like decision making. And so what this suggests is that these different components of the pupil response may index the recruitment of these different neural systems. And it gives us some confidence to say that, yes, pupil dilation may be tracking the neural systems that are important for listening in these adverse conditions. So the third thing I wanted to talk about is interventions. Can we alter listening effort to improve outcomes for our patients? So in my own lab, we have some evidence that listening effort can negatively impact daily life functioning. So what we have here on the plot here is, again, that activity that I showed you in the right anterior insula frontal operculum here associated with the cingulo-opercular network. Individuals that engage that region even more during difficult listening also reported greater subjectively experiencing effort. Those individuals reported difficulty participating in social roles, by which I mean they reported that it was difficult for them to go out with their friends, engage in situations that may potentially be distracting, busy, noisy, but things that are really important for maintaining a high quality of life. And indeed, there have been a number of studies showing that listening effort can result in poor memory for speech. Hearing loss that's untreated may give rise to listening effort that affects balance and overall poor quality of life. So there are some real life outcomes that make it important to sort of really get a handle on what is effort and what should we do to intervene. And so a point that I'm going to make is maybe not so intuitive, that we think about an intervention as something we want to minimize effort. We want to make sure that the task is as easy as possible. And actually that doesn't seem to be the case, as I'll show you in a moment. Really what we think should be the goal of an intervention is to optimize effort, particularly with respect to performance. And that's shown here on this little cartoon figure, that task demands may be harder or easier. And there's a really obvious relationship between task demands and performance. As things become easier, people tend to do better. But the relationship between task demands and effort is not so linear. So as things are really hard, people start giving up. Why should I invest any effort into this if I'm going to be doing so poorly? And so that's kind of demarcated by this red asterisk here. As hypothetically they're engaged in some sort of intervention or training, hearing aids, something like that, the outcome may be, in fact, that they sort of move up this curve, and the task of listening is actually becoming more effortful because now they're able to engage in situations that maybe they would have just previously given up in. And then ideally, once you pass that point, as task demands become even easier, then yes, effort may in fact decline. But the point here is to really think about where people are starting off from in order to make really solid a priori predictions about where we hope they're going to end up. So the first intervention study I'm going to tell you about is a speech perception training study with older adults with hearing loss. And we used a training protocol that's been used before, where people listen to words and phrases in sentences and background noise. They chose the word they thought they heard, and they get feedback. They do this for an hour, for 20 sessions. It's very boring. But these training programs have shown increases in performance over time. So we wanted to know, what is the impact on listening related effort of a speech perception training program? What we found is that training effects compared to a control group, we saw an early peaking pupillary response. So if you look here, again, I'm plotting pupil dilation over time. Our training group is in red and our control group is in blue. Pre-testing is dotted and follow-up testing is solid. And so what you can see is the shift in the peak between this red dotted line and the solid line. For the training group, there's a shift, quite a significant shift. And that's of a similar kind of magnitude as we saw in the previous study, showing a speeding up of the pupil response when we made the signal to noise ratio easier. So training may effectively improve the signal-to-noise ratio for people. But something that we maybe didn't expect a priori, but should have, is that there was also an overall shift towards larger pupil dilation, kind of the mean indicated here by this line, shifting up overall. And maybe we should have realized it because people were doing really poorly in terms of performance at the start of training, and there was a significant increase as they went along. And so in a later study, we followed up and said, is this really, the shift in effort, is it a beneficial thing? And so, we thought maybe that it's really about people being now able to engage in listening. What we did is for these individuals, we looked at their neural responses and behavioral responses on some standardized tests of vigilance and sustained attention, and found an association such that people who had a higher pupil response tended to be more vigilant and have greater sustained attention reflected in their behavioral and neural responses. The second type of intervention I'm going to tell you about is something I've been working on more recently, in particular neurostimulation, transcutaneous vagal nerve stimulation, which is a non-invasive approach for stimulating the vagus nerve via its auricular branch. In particular, the vagus nerve has projections to the locus coeruleus, and this type of stimulation, which can be delivered via an earbud with some electroconductive gel on it, has been shown to improve paired associates learning, has been shown to induce plasticity in auditory cortex with a pure tone learning task. And so our question was, is this something that can have a sort of effect on, in terms of the effort it takes to learn more complex tasks? And our focus was on learning Mandarin lexical tone. So for those of you that know Mandarin, know that the lexical tone changes the meaning of the word, and that it's really, really difficult for native English speakers to be able to use that information to distinguish among words. So what we did is we had a training program, again, one that we knew sort of worked behaviorally at improving lexical tone performance, and said, can we use this peripheral nerve stimulation to kind of boost that and enhance that? And if so, what are the consequences on the effort that it takes to learn this information? So we had a passive word learning task in which individuals who are native English speakers, completely naive to tone, to lexical tone, they listened to these pseudo-Mandarin words with different tones and were given associated English translations that they had to just passively associate. And this was embedded in a much longer learning paradigm. What we saw is changes in the pupillary response depending on what type of stimulation we gave people. So first in purple, I want to point out, this is the sham condition. So this was double blind, so people were not receiving stimulation even though they thought they might be. And what we're looking at here is the difference between the pupil response on the second day of training versus the first day of training. And you can see this sham group, it kind of hovers around 0. There's some drop off in the pupil response from day 2 to day 1, but it's pretty minimal. Then we had 2 other stimulation conditions. One that we call priming, where we just gave some people stimulation for about 10 minutes before they did the learning task. And that's in green right here. Again, it hovers around 0, not a major shift in the pupillary response. But when we presented stimulation in a time-locked fashion, right when the word was being listened to, we do see that that tends to change in a more dramatic fashion the pattern of effortful listening to those Mandarin tones. So what we see, the difference between day 2 and day 1 is that there's this much faster fall off in the pupil response when we give them this, what we call peristimulus stimulation. And that was marked and consistent across individuals, even though individuals had no idea whether they were receiving any stimulation or not. And so the takeaway here is it seems that TVNS boosted learning can have the effect of reducing listening effort for information that is typically very challenging. So the last thing I want to just touch on briefly is a question I hope maybe we can get more into is what is the relationship between listening effort and fatigue? So there's this assumption in our field that having to sustain high levels of listening effort should lead to the fatigue that we know that our individuals with hearing loss are reporting. That's sort of how I started this whole talk. And there's a variety of ways that people have tried to measure listening related fatigue: surveys, decrements in performance, constriction of the pupillary response. However, the relationship between effort and fatigue has really yet to be clearly demonstrated. There's maybe a weak correlation at best in this paper that I cite here, but there hasn't even really been a ton of research on it. And the problem, I think, parallels the problem with listening effort, right? So fatigue can mean a lot of things. There are multiple types of fatigue. There can be physical sources, mental sources, emotional sources, and it really depends possibly on the time scale that we're talking about. So are you talking about pupil constriction within a trial? Are you talking about fatigue across an experiment, fatigue at the end of the day, or are you talking about something that's more chronic? And the little bit of work that I've helped out on looking at fatigue-like effects, I don't even know if I should call this fatigue, is changes in the pupil response to 12 seconds of speech. So typically, all the studies I've talked to you about so far are single words that I present. But what happens when people have to sustain their attention to longer passages? So what we can see is shifts in the pupil size across time. We have them listen in both easy and hard signal to noise ratios. And we see that indeed, pupil size tends to fall off over time. But it does so pretty consistently for both the easy and hard conditions if you just look at the first block of the experiment. But when you start looking into the second block, you see that while people are able to still sustain their attention somewhat, when listening is a little bit easier, it falls off pretty dramatically in that harder condition. So there's really like an interactive effect between not just your ability to sustain attention within a trial, but then how that can deteriorate across the blocks of an experiment. So in summary, I hope I've convinced you that pupillometry reveals the time course of the interactive, auditory, linguistic, and cognitive demands that impact effortful listening. That individual differences in the pupillary effects are linked to activity in specific brain regions that support sensory and attention processing. And that changes in effort can be elicited with training-based and neurostimulation-based interventions as long as we mind the curve and think about where on that nonlinear function people are starting and how that might impact where they end up. And we have a long, long way to go in terms of understanding the relationship between sustaining your listening effort and ultimately the fatigue that we care about in our patients. So listening effort is multidimensional, and we can characterize some of those, at least some of those aspects with pupillometry and validate it with neuroimaging studies. And understanding the processes that underlie effort and fatigue is really going to be key to how we design our interventions and how we ultimately improve patients' quality of life. Thanks to my collaborators at the University of Maryland and Medical University of South Carolina, and to my sources of funding. Thank you for your attention.